Hello, Math 2 students. There are so many things in real life that are modeled by quadratic functions that today we're going to take a look at a few of them. The first problem says, the cables between the two towers of the Tacoma Narrows Bridge in Washington form a parabola that can be modeled by y equals 0.00016 squared minus 0.46x plus 507, where x and y are measured in feet. What is the height of the cable above the water at its lowest point? What are the domain and range in the context of this problem? First, we need to identify what our A value, our B value, and our C value are by looking at the equation. Our A value is 0.00016. Our B value is negative 0.46, and our C value is 507. Now that we know those values, let's take a look at the graph. When you look at the graph, the black lines are the x and y axis, which makes this point the origin, 0, 0. We know that our C value will always tell us what the y-intercept is. So we know that this point here is over 0 and up 507 because our C value is 507. Now the question is asking us to find how far the bridge is above the water at its lowest point. Well, if we look at the parabola, there's its minimum value right there. That's where it's as close to the water as it's ever going to get. That point is also the vertex. So if we can find the vertex of our equation, we will know when the bridge is closest to the water. So in order to find the vertex, we need to start out by using the equation x equals negative b over 2a. As you can see, I've substituted b and a into the formula for finding the x-coordinate of the vertex, and the x-coordinate of the vertex is 1,437.5 feet. Now I'll use the original function to find the y-coordinate of the vertex. And the y-coordinate of the vertex will give us our minimum value, and that will be the answer to the first part of the question. So I've substituted the A value in for A, I've substituted the B value in for B, the C value in for C, and I've substituted our x value that we found in the first step in for x. So the y-coordinate of our vertex, when you type that into your calculator, will be 176.375 feet. So if I round off to the nearest tenth, that will be a y value of 176.4. So the vertex of the blue parabola in the picture is 1,437.5, comma 176.4. The y value shows us the minimum or the maximum, and since our parabola is opening up, that'll be the minimum value, or in other words, in the context of this problem, that is the place where the bridge is closest to the water. So when the questions ask, what is the height of the cable above the water at its lowest point? The height of the cable above the water at its lowest point is 176.4 feet. Now we're going to add some details to our graph, and then we'll be able to find the domain and the range for this function in the context of this problem. So the first thing we're going to do is add the axis of symmetry to our graph. And the axis of symmetry is a vertical line that goes right through the origin. And our axis of symmetry on this problem would be x equals 1,437.5. But the important thing about the axis of symmetry that will help us on this problem is we know it can give us a third symmetrical point. So if this distance from the y-axis, the first column on the bridge, is 1,437.5. We know that the other column of the bridge, the other symmetrical point, is going to be 1,437.5 feet away from the axis of symmetry. So that makes this point at the top of the second column of the bridge 1,437.5 plus 1,437.5, or 2,875, 507. So we have our axis of symmetry. We know the points at the top of both columns of the bridge, and we know the minimum value by looking at the y-coordinate of the vertex. So first, let's start with the domain. Remember, the domain is a list of all x-coordinates of every point that could be on the graph. We would normally say that the domain is all real numbers, but in this problem, the domain is not all real numbers. So if we look at all of the x-coordinates of every point on the blue parabola in our picture, the smallest x-coordinate is going to be greater than or equal to 0. The biggest x-coordinate that we could possibly have is less than or equal to 2,875. For our range, that is a list of all y-coordinates of every point that could possibly be on our graph. The lowest part of the range we already figured out is 176.4 feet. So all of our y values will be greater than that. So we write y is greater than or equal to 176.4. And our parabola is not going to go up, up, up forever. Our parabola is only going to go up to 507 because that's the height of the tower on the bridge. So every y-coordinate of every point on the graph is going to be equal to or less than 507. And that is our domain and range in the context of this problem. Our second example says a group of friends is launching water balloons. The function f of t equals negative 16t squared plus 79t plus 5 represents the height in feet of the first water balloon t seconds after it is launched. The height of the second water balloon t seconds after it is launched is shown on the graph. Which balloon goes the highest? And part B, which balloon is in the air longer? Explain your reasoning. First, let's find all of the information that we can see on the graph to help us answer part A, which balloon goes the highest, and part B, which balloon is in the air longer. For part A, to find out which balloon goes the highest, we want to find the maximum height of the second balloon. So when we look at the graph, if we can estimate what the vertex is, the y-coordinate of the vertex will tell us our maximum height. Since our parabola opens down, then it will have a maximum height equal to the y-coordinate of the vertex. You can see that I've estimated the vertex to be 2.8, 130. On the x-axis, we're measuring time, and each square on the x-axis counts as 1 second. So I'm just estimating that our vertex is a little bit in front of 3 seconds. So I'm making a guess that 2.8 seconds is the right amount of time that it would take for the water balloon to get to its maximum height. And then on the y-axis, every square counts as 25 feet. So it looks like our water balloon goes a little bit higher than 125 feet. So I'm estimating that the maximum height of the water balloon will be 130 feet. So for part A, the second balloon will have a maximum height of 130 feet. For part B, they want to know which balloon is in the air longer. Well, we're going to need to take a look again at the x-axis, and remember they're counting by ones. In order to estimate when the balloon is no longer in the air, we need to find the time at which the balloon reaches height of 0 on its way back to Earth. So this point right here would have coordinates 5.8, comma 0. So if 5.8 seconds pass, and that's an estimate, I can see it's a little bit less than 6 seconds. When 5.8 seconds pass, the balloon will have a height of 0, which means that the balloon has been flying through the air for 5.8 seconds. So when we get to part B of the problem, when we're trying to decide which balloon has been in the air longer, we know that the second balloon spent 5.8 seconds in the air. Well, we could get the information about the second balloon by reading the graph that was given in the problem. To get the information about the first balloon, we're going to need to use the equation. So the first thing I'm going to do is rewrite the equation so that it's not in function form and identify the A value, the B value, and the C value. The way that we found the maximum height of balloon number 2 is we found it by finding the vertex, and the y-coordinate of the vertex was the maximum height. So now we're going to have to find the y-coordinate of the vertex of our function. So we'll start by using the equation x equals negative b over 2a, and we'll put in 79 for b and negative 16 for a, and we'll see what the x-coordinate of our vertex is. When I put negative 79 over 2 times negative 16 into my calculator, I get 2.46875, which I'm going to round off to 2.5 seconds. Now to find the y-coordinate of my vertex, which will tell us our maximum height, I'm going to put my A value, my B value, my C value, and my X value into the function, and I'm going to solve for y. So negative 16 times 2.5 to the second power came out to negative 100. 79 times 2.5 came out to 197.5, and my C value is 5. When I add those together, I get 102.5 feet. So for my first water balloon, the parabola that describes its flight has a vertex of 2.5 seconds and 102.5 feet. So in 2.5 seconds, the water balloon reached its maximum height, and its maximum height was 102.5 feet. Well, we already found out that the second water balloon goes to a maximum height of approximately 130 feet. To answer part A, which balloon goes the highest? The balloon that goes the highest is the second water balloon. For part B, we need to find the time when water balloon number 1 has a height of 0. So in this problem, y is the height and t is the time. So we need to find t when y is equal to 0. The way that we know to solve this equation, y equals negative 16t squared plus 79t plus 5, is by factoring. The first thing I'm going to do, because my a value is negative, is I'm going to factor out the greatest common factor of negative 1. Now I'm going to break 16t squared minus 79t minus 5 into its binomial factors. So my first binomial factor is 16t plus 1, and my second binomial factor is t minus 5. Now we need to use the zero product property to find the value of t in both binomial factors. So it turns out that the first binomial factor, t equals negative 1/16 of a second, and the second binomial factor, t is 5 seconds. So how can there be negative time? Well, in this problem, if you notice, the c value is 5. So the water balloon starts 5 feet off the ground. If you think about the x-axis and the start of the water balloon's flight, it's never at 0. So you would need to go to negative time to find the place where the water balloon was at 0 if you're looking at the start of the problem. That does not matter for this problem. What does matter is t equals 5. Our balloon was in the air for 5 seconds before it reached a height of 0 on its way down. The second water balloon was in the air for 5.8 seconds, and our water balloon, the first water balloon, was in the air for 5 seconds. So the answer to part B of the question is that the second water balloon was in the air for a longer amount of time.